Uh, Hello there again. This is our third look at Year 12 Discrete Maths for Chapter 1 in Year 12 Discrete Maths. So we're going to look today at the pigeonhole principle. I thought I'd get onto this last time actually, but we never did. We got stuck on partitions for longer than I thought. So here's the third one in the series of PowerPoints. And what we're looking at today is well, it strikes me it's fairly obvious, but you'll make your own mind up, I suppose, when you see it. Um, so let's have a look at this anyway. So the pigeonhole principle says that if we've got a collection of pigeonholes, and you'll notice this is what pigeonholes really refer to in the workplace, at least, they are a collection of boxes where traditionally, if you got letters to different members of staff, you'd put, Bob Smith's letters in here and Angela Smith's in there maybe, and each person would have a different place to put their letters, and then you'd go along one day at a time and you'd find your letters and you'd go and read them. These days with emails it's slightly less relevant, but the principles from this now is going to be used in maths. So the pigeonhole principle says that if we have m letters that you're going to put into your pigeonholes on a particular day, and it says there are n pigeonholes, and importantly they're basically saying we've got more letters than pigeonholes. That's what that says. If the number of letters m is bigger than the number of pigeonholes n, then there must be at least one pigeonhole with two or more letters. Now this strikes me as blatantly obvious. Here I've got 9 pigeonholes that I could put letters in. If I have 8 letters, then fairly obviously I could put them in there if I wanted to, one in each. And I'd even have a spare box. Now, if I choose, if we've got one particular member of staff who's really popular, I might get 6 letters in there. But I don't have to do that as a general rule. If there are 8 letters, then what I would get is I'd be able, if I was so inclined, to put them into 8 different boxes, and therefore there'd be one left over. But here's the logic of this. If I have more than the number of pigeonholes, if I have 10 letters, then by definition, if I put one in each of all of these, I've got 9 pigeonholes. So by definition, one of them's got to have a 2. And so whichever one it is, that's all the pigeonhole principle says. So it's dressed up as a fancy rule, but really it's blatantly obvious. So let's look at this. Now I've got an example there. It says 15 letters into there. Well, now if I've got 15 letters, I'm going to have lots of things. For instance, I might have a 4 here now. What's that adds up to? That's 6 plus the 7. I reckon I've got another 2 still to go. I'll have 3 in there. 7, 9, 10, 11, 12, 13, 14, 15. Hurrah, I've managed to do it. Notice, though, the idea of this, if I have 15 letters, 9 pigeonholes is not enough. 10 letters, as long as my number is bigger than the number of pigeonholes, then I'll definitely need 2 or more letters in each one. At least one of them. So here's a proper exam question on this, and we'll see how it goes. So it says Mo eats exactly 6 donuts in 4 days. Doesn't sound like a pigeonhole principle question, but clearly it's going to be. What does the pigeonhole principle tell you about the number of donuts Mo eats each day? Well, straight away I'm thinking if she eats 6 donuts in 4 days, she must eat more than one on at least one day. That's what the pigeonhole principle tells us. So it's not dressed up to be the same. I can't see any boxes drawn here, but that's the same idea. 4 days, 6 donuts. She must eat at least one day. She must eat more than one. Now Mo, it says, eats exactly 6 donuts in 4 days, eating at least one donut each day. Okay, that says the same thing. Show that there must be 2 consecutive days or 3 consecutive days in which Mo eats a total of exactly 4 donuts. I suppose you could do this by listing. So how many days we've got? We've got 4 days. So we've got these 4 places here. We could just, they've got to add up to 6, haven't they? So I'm thinking 1, 1, 2, 2 sounds reasonable. Now it says on this there must be either 2 consecutive days or 3 consecutive days in which Mo eats a total of exactly 4. And straight away I look at this and I think, yeah, that's got a 4 there. So 1122, can I list this any other way? Well, I could, for instance, get 1113. Seems reasonable. I could get, and I'm just listing all the different ways of doing it. I could, I suppose, get 3111. I could get 2211. I could get the ones and the twos in a variety of places. 1 2 1 2. I suppose you're trying really to do this in a logical order. I don't think I have particularly, but one a 2, a 1, a 2 and a 1. Let's stick with these 2s and the 1s. Have I done them all? I've got 1 1 2 2 and I've got 2 2 1 1. I've got the 2s together. 2s, I think I've done them all. So the 3s, I've got the 3s at the front and the end. So I reckon I could probably do 1 3 1 1 and 1 1 3 1. I don't think I could get to 6 in any other way if I eat it 4 times. So I reckon on each of these, that's got a total of 4 there. That's got a total of 4 there. Now it says, well, that's got a total of 4 there. That's got a total of 4 there. Well, this is not quite the same, but it says 3 consecutive days. So I reckon that's the 3 consecutive days. And so is that. And that's 4. And that's 4. I mean, I don't think this is particularly hard. Mo eats exactly 3 identical jam donuts and exactly 3 identical iced donuts over the 4 days. The number of jam donuts eaten is on the 4 days is recorded as a list. For instance, 1020. The number of iced donuts eaten is not recorded. Show that the 20 different such lists are possible. Now, again, you could list them. I suspect there's a better and quicker way of doing it. So just thinking about what they've done, they've said 1020. I suppose that could have been also in any order. I could, for instance, have done 0 0 1 2, and that would have been the same number of jam donuts eaten. Now, I suppose what I want to do is work out how many different ways of doing 0 0 1 2. And that sounds to me like we've got 4 numbers, 4 factorial, and because 2 of them are the same, we divide by 2 factorial. So 4 factorial divided by 2 factorial, and 4 factorial is 1 times 2 times 3 times 4, which is 24, divided by 2 is 12 ways of doing that. Now, what other ways are there of doing this? Now, I suppose I could go 0 0. I've only got 3 of these things, so I could go 0 3 and just eat 3 in one day if I so choose. Now, if I do this, I suppose I can use the same logic. There's 4 numbers, 4 factorial, and now there's 3 numbers repeated, so divide by 3 factorial. And if you do that, you get 24 divided by 6. You only get 4. So what other ways of doing this are there? I suppose I could go 0 1 1 1. And again, that would be 4 factorial. There's 3 numbers repeated divided by 3 factorial. And that would be, again, the same answer as there. That's 4 more. And actually, that adds up to 20. And I don't think there are any other ways of doing this. So I think I have got 20. And I'd write a little sentence to convince someone that I've done them all. And let's see what I've got answers for this. Yes, I have. There are, yeah, that's basically what they've done. They split it into these different ways, and they said there's 12 ways of doing that, and they've shown the method and 4 and then 4. So that's much better than listing them all. So the next question then is, well, on the face of it, doesn't look anything like the pigeonhole principle. It says 10 points are placed in a square of area 2 square centimeters. Now this area is 2. So I suppose this is root 2 times by root 2. So when I times the length by the width, it gives me an area of 2. But it says I put 10 points in this square. and it says show that there must be at least 2 points which were within 2/3 of a centimetre of each other. Now, on the face of it, this has got nothing to do with what we're doing or been talking about, but I suppose we know we're talking about the pigeonhole principle, so we know it's going to be about that. So this is going to be something to do with the pigeonhole principle, and for that reason, here's a little hint for us. And my hint, basically, if I can make it do it. There. Divide the square into 9 equal small squares. There's my hint. And suddenly it looks more pigeonholey. So suddenly I've got a chance. Now, if this is the case, that this is now pigeonholes, so I know if I split it like this, I suppose, by my definition, I've got 9 places. I can quite easily put 9 points in there. And I suppose here's the key. This is why I've split it into a 3x3, because it says 10. And 10 is one more than 9. And so now I've got 3x3 kind of squares. But bear in mind, really it's root 2. So if this is root 2 divided by 3 for each of these here. And likewise, going down, it's root 2 divided by 3 for each of them going down like that. Within each little square, that's the actual distance from top to bottom. And I suppose what I need to do is to find what's the at least 2 points which are within 2/3 of a centimetre. So the furthest these 2 points could be would be that distance there. And I suppose I could use a bit of Pythagoras here. I could do root 2 over 3. I could square it, and that's that distance there, and the distance across there is the same as that. So that's also root 2 over 3 squared. And this is Pythagoras, isn't it? It's a squared plus b squared will give me the c squared, the distance of the diagonal. So if I do this, that goes 2/9 plus 2/9, which is 4/9. So this diagonal obviously that's equal to c squared. And so my c is the square root of 4/9, which is where the 2/3 comes from. Now, so that tells me this distance here, I know, is 2/3 of a centimetre. Why does that matter? Look, because the pigeonhole principle tells me if I've got 9 points, I could put one of these into each of these. And I'd be able to do that so that all of these points that I'd put in, I could find 10 points in there somehow. 9 points in there somehow. All of those points would be at least 2/3 of a centimetre away from each other. But of course, as soon as I get a 10th point, as soon as I get a 10th letter, if you like, I can put them in here somewhere. But if I've got 10, I've got to put another one within the same square. That's what the pigeonhole principle tells me. And that means it's got to be less, because I can't put them at their optimum distances apart, which would be on all the diagonals. And so suddenly, because of the pigeonhole principle, tells me I will need to put 2 of these in at least one square. That tells me there must be at least 2 points which are smaller in distance away from each other than the 2/3. They can't go on these diagonal points. And suddenly that makes sense. Let's see what the answer says. Root 2 over 3, there are 10 points, so pigeonholes, you can see what's going on here. So here's a question which I think is surprising, really. It doesn't look as if it's anything to do with pigeonholes, but it was. And I think this is probably the hardest type of question you could get on the pigeonhole principle, because you're trying to work out that it's the pigeonhole principle, even though it really wasn't. And I suppose that was similar to that on our last question. We had the exam question, didn't we, which was about Mo eating donuts. Now, the clue there was in the question. It told us it was about the pigeonhole principle. But this one really didn't. It just expected us to spot it much harder. Now look, we've done exercise 1A.1, 1A.2, 1A.3. We are now going to look at this OCR Cambridge book questions and look at exercise 1A questions from it. So I hope that's useful, and that's chapter 1 for year 12 on these sort of chapter 1 topics. That's all the work for it, and now it's just a case of practice. So thank you very much. All the best.